In this video, we are going to discuss chapter 5 from your textbook, Introduction to Factorial Designs. So, first we will discuss general principles of factorial experiments. Then we will talk about the two-factor factorial with fixed effects. Actually, this first video, I will exclusively focus on general principles, and in the next video, we will discuss the two-factor factorial. Also, in the next video, we will discuss how to apply analysis of variance for factorial experiments. Then the chapter also discusses the extensions of these particular statistical model factorial designs to more than two factors. Other topics that we are going to discuss is, for example, the different how to differentiate between quantitative and qualitative factors, and how our analysis techniques such as response curves and surfaces will change based on the type of factors that we are dealing with. So here are some basic definitions. Let's say we have a two-factor factorial experiment, which is shown in this chart. Factor A is on x-axis and factor B is described on y-axis. Each factor has two levels, low level and a high level. Uh, Same for factor B, low level and high level. Sometimes we also call them minus one, plus, minus and plus, or sometimes you will see minus one plus one, minus one plus one. So these are basically coded variables. They can be anything. This is a hypothetical data. For example, in from our chapter one, that golf experiment, our factor A can be the type of driver that we use in the game of golf, right? Regular driver versus oversized driver, right? We can also on factor B can be the ball, balata ball or three-piece ball. So depending on the problem, they can be different factors, but both of the factors have only two levels, and so that makes a four unique experiment. And we have this hypothetical data shows here the response variable values that were collected from the experiment. So 20, 30, basically this experiment here is low level of factor A minus 1, and high level of factor B, so plus 1, minus 1 plus 1. Similarly, this one is high A, high B. This one is high A, low B, and this one is low A, low B. And we have these results of our response variables. So to calculate the effect of factor A, what we need to do is y bar A plus minus y bar A minus. So basically take the average of readings when A is high, A plus, right? So 40 and 50, this side is A high and this side is low high. So if you take the average of this side and subtract average of this side from that, you will get the effect of factor A. So uh, 40 plus 50 divided by 2 minus 20 plus 30 divided by 2, that gives us a 21. Similarly, to find the effect of factor B, we take y bar B plus minus y bar B minus. So we take the average of, this is a high B side and this is low B side. So we take the average of the response variable values on high B, and we subtract the average of response variable values of low B from that to see the effect of factor B. So, by after doing the calculations, we see that the effect of factor B is 11. Now, this effect shows the magnitude, how big the effect is, as well as the direction. So, for example, uh, when you increase factor A from low to high, you see increase of 21 in the response variable, right? Here, uh, if it was if you, let's say, if by going from B minus to B plus, if the response variable value decreases, then you will get a minus here. So both have positive effects. Now the last thing is to look at the interaction effects. Uh, is there any interaction between factor A and B? And this is very important. In all the previous chapters, we did not talk about factors interacting with each other, right? Uh, because as you have studied, for example, chapter 3, it was about a single factor analysis of variance. So there was only one factor, there was obviously no interactions, right? In chapter 4, where you talked about a randomized complete block design, there was a nuisance variable and there was a main factor. We did not talk about the interaction between them. But now, in this chapter, we have to talk about the interaction effect, because sometimes interaction effect can be higher than the actual primary effects of the factors themselves. And if we ignore that, I mean, a good design of experiment statistical model uh, can capture the interaction effects. A failure to capture the interaction effect will basically lead to failure in your design of experiments. So very important. So how do we capture interaction effect for our hypothetical data? So we take this diagonal, okay, 50 and 20, this diagonal, take the average of those two, 52 plus 20 divided by 2, and then take these two diagonal values, 30 plus 40 divided by 2, and take the difference of the two averages. We got here -1. So as you can see, its negative magnitude is very very small as compared to the effect of main factors, and it's a negative effect. So now the next question is, are these effects that we have shown in these numbers, are they statistically significant or not? Of course, the bigger the number is, the more significant the effect is, and the closer we are to zero, that may be just noise, there may not be any interaction effect. So in this case, looks like there is not much interaction between the two factors. If same can be shown graphically if you plot them, like response values versus one of the factors, right? Factor A in this case, and minus low level of factor A and high level of factor B. Then you will see that this line represents the minus b, the how the factor a value, the response value changes when we are moving from low level of factor a to high level of factor a, where factor b level is constant, b minus b minus, right? And here b plus b plus. What is a peculiar thing that you will notice about this plot is that these two lines are almost parallel to each other, and that is the indication of no interaction effect. If, and I will show you another graph where how these lines will show up when there is a significant interaction. But in this case, since the two lines are parallel to each other, we can say that there is no interaction effect, or a very insignificant interaction effect. The slopes of these lines stay the same. So before I discuss this second slide, let's look at some plots for this first problem. Okay, so here we performed a regression analysis on the this data here, and based on the regression analysis using the least square feet, here is our regression model, and for our to fit that model for this problem, what values do we get? So let's see. Y is equal to beta 0 plus beta 1 x1 plus x1 is the factor A, basically we are referring to, plus beta 2 x2 factor B, plus beta 1 2 x1 x2 interaction effect, plus epsilon, which is standard error, right? And when we use the least square feet, uh, here is the expected value of response variable y hat is equal to 35.5 plus 10.5 x1 plus 5.5 x2 plus 0.5 x1 x2. That the regression model is this particular regression model, right? Now, if you look at the coefficient of factor A, x1 and x2, and coefficient of interaction, they are basically half of this main effect of factor A and main effect of factor B, as well as main effect of interaction. So that is always the case when in the two factor factorial, when our factors are coded -1 and +1, low and high value. Uh, Now, once again, you can see from the regression analysis that this particular term 0.5 x1 x2 is basically we can ignore it, right? It's insignificant. The coefficient is so small. So we after removing this, let's remove this term, and then our approximate model is 35.5 plus 10.5 x1 plus 5.5 x2, and then we can plot this. We can create the response surface plot where we have the three-dimensional response surface plot. We have x1 factor A on this axis, factor B x2 on this axis, and our response variable is on that axis. So if you look at this plane, this is a flat plane, right? That's another indication of there is no uh, if there is no interaction effect because the surface is flat. And uh, if you then plot it different way, like it is called as control, this is called as the response surface plot. And if you look from the top, if you look from the top on the response surface plot, what you get is the contour plot, plot of x1 versus x2, and response. These are the lines of your response values. So any combination of x1 and x2 on this line will give you the same response, 22. Any combination of x1 and x2 on this line will give you the same response, 25, and so on and so forth. So the flat plane in the response surface and the lines, once again, the contour lines are parallel to each other. They are not curved lines, right? So these are straight lines. Those are all indications of no interaction effects. In fact, there shouldn't be any in these because we removed the interaction term uh, from the this equation, and then we use this modify equation to create these plots. So that is that. Now let's look at another example where there is a significant interaction. So again, this is a hypothetical data, factor A, factor B, just like last example. We have some values here, right? And we look at the average effect of factor A, which is y bar A plus minus y bar A minus, right? This side, average of this side minus average of that side, and that's 1. So very small effect. Then factor effect of factor B, average of this side minus average of this side is actually -9 in this case. That means when you move from low value of factor B to high value of factor B, your response value actually decreases, -9. So negative magnitude is high as compared to effect of factor A, and the direction is negative. And then let's take a look at the interaction effect, which is the average of these diagonal numbers minus average of these two diagonal numbers. So that is a massive effect, right? Interaction effect is it's bigger than the main effects of the two factors, and direction is negative. So what can that tell us? If you plot them, response versus one factor, factor A, you will see that the lines, the B minus line and B plus line, they are actually crossing each other. They are not parallel anymore. They are crossing each other. That means when the lines are not parallel, when they are crossing each other, we we can say that that's an indication of significant interaction. What it is saying is factor A is not that important, but when you uh, go from minus B to plus B, you see significant with the same. Uh, for example, uh, if you when you go from factor a low value to factor a high value, when b values are negative, your response is increasing. But when uh, when your b values are positive, your response is decreasing. That means uh, interaction between a and b is more significant as compared to the individual effect of factor a. Actually, individual effect of factor a is so tiny, probably that's a noise, right? So we can even ignore that. That means there is a no effect of main effect of factor a. So now this plot here, that is not for this problem. That plot is made by just adding a hypothetical interaction term to this regression model. We just added an significant interaction term 8x1 x2, which is basically the half of if main effect, right? 10.5 plus 5.5, the half of that is approximately uh, that much interaction we added. And look what that does to the response surface curve. uh, because of this interaction, now the response surface curve is twisted in it's not a flat anymore, right? So that's indication of curvature. The curvature is an indication of interaction. And if we look at the contour plots, x1 versus x2 or a versus b, uh, those are not lines anymore. Those are actually the contour lines. How basically that plot is the how this plane will look like looking from the top, right? So those are line curves. That's indication of curvature is always an indication of interaction. uh, Also, one thing you'll notice that this is a uh, special curvature type. It's not like a mount type. That mount type will happen only if we have a quadratic terms or cubic terms. But this is some twist in the plane because of this added interaction term. So that's how the effect of interaction can be shown in various plots. So now I will stop this video here. In the next video, we will actually look at an interesting numerical problem, and we will see how we can apply analysis of variance techniques to a two-factor factorial problem. So I will stop this video here. Thank you.